Hi, my name is Irene Lee, and this is my Lab 4 Oscillations presentation. So to start is my introduction. So for this lab, a mass is attached to a fixed spring and is stretched and then released. Using Tracker and the provided video, I was able to plot the position of the mass at different points in time. And then using GlowScript and the provided code, I was able to change variables in order to predict the motion of the mass based on the energy principle, momentum principle, etc. And then I compared my GlowScript data to the observed motion from the video. And then some lab assumptions would be the fixed end of the spring is located at 0. There's no friction, and then the mass is 0.402 kilograms, and the spring's mass is negligible, and then there's no energy lost. So here's some fundamental principles. First is Newton's second law, where the system's change in momentum is proportional to the net force applied. And then secondly is the energy principle, where the system's change in energy is the sum of work done by the surroundings and thermal energy exchanged with the surroundings. And then lastly, here are some forces as well. And then here are the initial conditions. So first is the mass is equal to 0.402 kilograms. The initial position is negative 0.020033 in the x component, negative 0.84990 in the y component, and then 0 in the z component. And then the initial velocity is just 0 meters per second. And then time is 1.5 seconds. K is equal to 6.3. And then Fg is equal to Fs. Mg is equal to Ks. And then S is equal to L hat minus L naught. L naught is equal to L hat minus Mg divided by K. And then L is equal to 0.12 meters. So for the code, we first initialize the initial conditions, and then we use the physics principles to calculate the needed components of the spring, and then we calculate the total energy components. So here below is some of the code that was used. And then here's the rest of the code that was used. And then here are just some graphs that were generated. So to the left is the change in energy versus time graph that shows delta K, delta U graph, delta U spring, and then delta E. And then to the right is the x position versus time and y position versus time graphs. So for our analysis, we found the energy principle is satisfied, and then the change in energy is equal to 0. This was a closed system, and the oscillation period is y is 1.5 seconds and x is 1.6 seconds. Right, and then here is our conclusion. This lab was successful because the code in GlowScript proved to be an accurate prediction to the real-life motion on the mass spring system. No surroundings led to change in energy equals 0, hence the energy principle was satisfied. And then there are only some small discrepancies on the graphs, and this is mainly to do with plotting and tracker and maybe some malfunctions in the exact position in real life versus the tracker data. And then lastly, an alternate experiment that could be done would be to use a more precise tracker, take friction and drag into account, and then using more tracking points and etc.